Ready? So, hi. Here we are. We're doing some dynamics calculations for tomorrow's lab. The lab tomorrow is rates of reactions, but 80% of it is solution preparation. So if our solutions are correct, the lab is straightforward. If they're not correct, then none of the lab works. So instead of doing this all as a pre-lab lecture, I'm just making a quick recording, and I'll send it to you guys, and you can take a look at it. So the first step is, if you remember from the pre-lab, there's really two sets of calculations you're doing. One for stock solutions, and then another for reaction mixtures. So what I have here are the three stock solution calculations. Now, I think you can do these on your own. So for the thiosulfate, you're using solid sodium thiosulfate pentahydrate. Okay? So you can do this one on your own. The molarity you're looking for is 0.04. You're doing this in a 50 milliliter volumetric flask, which has 4 significant digits, 50.00. Converted to liters, multiplied by the molar mass of sodium thiosulfate pentahydrate, which you should have, and I wrote it down somewhere, it's 248.2 grams per mole. So you should get somewhere around half a gram. So tomorrow you'll go into the lab, you'll go into the balance room, you'll get about half a gram, you'll write that down, you'll dissolve it in 50 milliliters of water exactly, and then you'll back calculate a more precise molarity. That's solution preparation. So that's good. So the second solution and the third solution are both by dilution. So you're given in both cases, a stock solution, and you're just making another stock solution. The molarities are both 1 to start out with. Now we'll look on the bottles tomorrow. They may be slightly different than 1, but for this, that'll be fine. So the initial molarities are 1. Then for the iodide solution, the volume that you're taking is half a mil. You're solving for the second molarity, and if you add up all that other stuff in the buffered iodide solution, the final volume should be 21.9 mils. Kind of an odd volume, and then you do the calculation in scientific notation 2 times 10 to the minus 2, and I'm carrying an extra sig fig. Because really, technically, I think we can get 2 sig figs there. So we should be good on 2 sig figs. Now again, you can do that on your own, just show that that's right. The peroxide, hydrogen peroxide, very similar. You're starting out with a solution of 1 molarity, you're taking 3 mils of it and dissolving it into a total volume of 20, and you can do that on your own. I'm showing you scientific notation here because I think it'll be useful when we get to the reaction mixture table. So those are the stock solution preparations. Let's go ahead and take a look at the reaction mixtures, and you can do these on your own, and then we'll fill the table in tomorrow when you come in. I think what I'll end up doing is writing a blank table, maybe have a couple of you fill in the answers, and we'll resolve any problems that you have, and then we'll just get started on the lab. Okay, so the table, we're recording a couple of different things here, which is interesting. We're using thiosulfate as our indicator of the speed of the reaction. So the concentration of the thiosulfate, if I remember the lab right, you're using the same volume each time, so this is going to be a constant concentration. Okay, we don't want to change that. So that will be a constant concentration. Now that's not a reactant. That's not one of our reactants. That's just what we're using to determine the rate of the reaction. So you'll do the reaction mixture, and when the solution turns blue, you'll record the time in seconds. Okay? To get the rate of the reaction, you take the concentration of the thiosulfate divided by the time, and that will be your rate of reaction, your initial rate of reaction. Now that's different than the textbook. The textbook would just give you a column and it'll say rate equals here, here, and here. You don't have to calculate the rate in the textbook problems. Here we have to calculate the rate. So that'll be your rate. So you can even label this rate of reaction, 1, 2, and 3. What we're after then is how is the rate dependent on our 2 reactants, iodine, and I can put the units here, but when you use brackets, that usually means molarity. So molarity, molarity per second, molarity. Okay, So now this table should start to look familiar, because we're going to systematically alter one reactant and leave the one constant. I don't remember which order it is. You'll figure that out, okay? And then see how that affects the rate of the reaction. All of these concentrations are using the dilution equation. So I'm going to kind of leave this up to you. We're applying the dilution equation again, but you have to use all of your M1s are going to be the M2s from the previous. So it gets a little confusing. So you use your stock solution concentrations over here. Those will all be that you just made. So the M2s over here become the M1s over here. Okay. M2 is what you're solving for. And then V1 and V2 are, well actually V2 is really easy. If you look at that, I'm pretty sure all of these are 10.00 mils, I think. And then just read through the recipe. How much iodine do you use in reaction mixture 1? How much H2O2 do you use? And then fill in this table. Oh, and then also how much S2O3. We need that too. But I'm pretty sure that should be constant. So let's see if we can fill that table in for tomorrow. The other little safety tip I can give you, not really safety, just convenience, is say all these are something times 10 to the minus 3. I don't know what they are off the top of my head. But you can put up here in parentheses times 10 to the minus 3 and then just write the actual number in. I don't know what it is. So that'll make the interpretation of the table just a little bit more aesthetically easy to do. Rather than putting in the scientific notation in each cell, you put the scientific notation part as part of the unit. Do you have any questions? Make sense? Cheyenne, it makes sense? Mm-hmm. Okay. So that's it.